I'm actually going to construct this step by step in another video, but this will be a briefer video indicating how you would construct the product function f times g for a function f and a function g given the graphs of the two functions with equal equal scales on the x-axis, congruent scales on the x-axis. Okay, so first of all, for a typical x value, let's take this x value here. And it's the same as the x value up here. So the function g takes a value that's represented by the length of this line, and the function f takes a value that's represented by the length of this line. Well, when we multiply f by g, then how big is the result? How can we represent how big the result is if we've got the size of this one and the size of this one? Well, the answer is if we construct a rectangle, one side of which is this length, and that's the rectangle I've constructed here, and another rectangle whose, and on the same rectangle, the other side, side perpendicular to that one, has this length, then we have a rectangle whose area represents this times this. So the area of this rectangle represents the value of f times g. Okay, well, now if we do that for every one of these x values, we're going to get a series of rectangles. Let's look at how this series of rectangles evolves. Okay, so for the first x value, we note first that the y value here is negative. So we're going to put a negative in front of the rectangle that we construct. Now we could take a compass and we could mark 2 points that far apart, representing the value of f, and we put a minus sign out here to remind ourselves that the value is going to be negative, and we see that because the value of g here is clearly positive, right? So we construct a rectangle with this width and this length. And the area of that rectangle represents f times g for this value of x. Then we do the same for this value of x. The value of g is this, the value of f is this. Now they're both positive, so we mark that as positive, and we construct one side of this length and another side of this length. And I haven't done that real well. I didn't use a compass and straight edge and any such thing to construct this, but you get the idea. And then I constructed this rectangle, which I explained originally. Now I construct this one. Now it's got, the purple line is getting longer and longer, but now the orange line, since the values of g are getting smaller, is going to get shorter and shorter. And down here it gets shorter and shorter, but it's negative, right? So we put a negative in front of this rectangle. Now if we were to continue, this would continue going more and more negative, this would continue going more and more positive, this would get bigger and bigger, but the result would be negative, giving us larger and larger negative numbers. We also ask, well, where is it that the value of the function might be 0? It's always good to try to find those values, and it's fairly easy to see what happens. Between negative and positive here, we got a point where this function takes a value of 0, which is going to give us a rectangle with no width. So the area of that rectangle, of course, would be 0. We wouldn't even really have a rectangle. We'd just have a line segment with, only one dimension. So in two-dimensional plane, it has no area. And function g is 0 here for this x value. So that means that over here in this graph, we can put a red point between these two x values. That would be like right here. And between these two x values, that would be like right here. And we know that f times g is going to be 0 at those points. Okay, well then, we, one way or another, work out a way to compare the areas of these rectangles. One possible way would be to split the rectangles up into little squares, all the same size. Now, it's unlikely that the areas or the dimensions of these rectangles would be amenable to that sort of thing, but that would be a place to start making estimates. Another, we could split the rectangles into thin strips and put the strips down consecutively, thin strips of the same width for all rectangles, and compare the areas that way. So by one kind of reconstruction or another, we could get some sort of reasonable comparison of these areas. And of course, these areas are what we're graphing on this graph, because these areas represent the values of f times the values of g. One for each of these 5 x values. And we then make a plot. Okay, we think that this and this are the biggest rectangles. That's pretty, and it's hard to tell which one's bigger, so I just kind of said, okay, this rectangle, which was obtained for this x value, which is this x value, has some area. This rectangle, if it has about the same area, well, this rectangle corresponds to the next x value over, so I just put it down with about the same y value, okay, same area. So I've got these 2 points. I've got over here a point with a negative area, and it's not a totally insignificant area, so I just put that about here. This one's even thinner than this one, so I gave it a little less, a negative area of a little less magnitude. And then this one kind of in between, this one and this one. A significant portion of this one, but clearly less. So I had points here, 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 and here, plus the points in the x-axis here. So when I went to graph these, I asked people, what kind of shape do you get? And everybody kind of said, looks like a parabola. Okay? Well, it turns out that it is a parabola, because a straight line function is a linear function. It's like 2x plus 5, something times x plus something else. And this one would be, well, it'd have a negative slope, so it'd be like negative 4x plus 3 or whatever it is. Okay? And if you multiply 2 of those things, you get a quadratic expression. So without going too deep into that, if you've been through that sort of thing, if you've got at least algebra, if you just had just algebra 1, that might be a little vague, and I don't want to belabor it. I'll just tell you that if you do 2 y equals mx plus b times functions with different values of m for the 2 functions, different values of b, you multiply them out, you're going to get something with an x squared, something with an x, and